This is the second video regarding the analysis of statically indeterminate structures, and I'm going to talk today about the approximate analysis of rectangular building frames, and we're going to talk about the analysis for vertical loads. Okay, let's go and see how we are going to go through this class for today. First of all, this approximate analysis of rectangular building, I'd like to highlight this, which is the rectangular. Okay, we are talking about rectangular and building. So this is the special case that we're going to talk about, which is like something like similar to this. Okay, I mean that's similar to a frames for rectangular buildings. So we're not going to talk about other buildings, which is not regular, for example. So we're not going to talk about like structures that is similar to this one, for example, which is not regular, but we're going to talk about regular ones where that we can apply our approximate analysis. Remember that approximate means that we are going to use some engineering judgment, and we are going to use it in order to make it easier for us to make the analysis that we are about. The analysis here means that to find the shearing force, the shear force, this is number one, number two, the bending moment diagram, and the axial force for all members. This is what the meaning of the analysis here. So now this is the detailed meaning of each word in our title, approximate analysis. So again, approximate means that engineering judgment that is going to be used, and this engineering judgment is going to be based on some assumptions that we are going to start with. So this is why the next slide is going to talk about the assumptions. And we understood the meaning of rectangular, and this is for buildings, and the frames. We are going to talk about frames, 2D frames. Okay. Let's go to the main assumptions. There are some assumptions that we want to go through, okay, in order to make our analysis to be simple, and as long as we are going to assume something, it is going to be approximate. Okay, so this is the assumptions. We are going to address them now in order to make an approximate. So it is not accurate. It's not 100% accurate. There are some approximation is accepted here because of the assumptions that we are going to make. Let's go to some things to understand first, and after that we can go through the rest of our video. First, we want to understand the meaning of redundancy. I'm going to repeat this word many times. Redundancy means that the degree of indeterminacy, and this is the difference between total number of unknowns and the number of equilibrium equations. So if you are going to have unknowns, if we have like 4 unknowns, for example, and we have 3 main equilibrium equations, so 4 minus 3 it equals 1. So our structure in this case is going to be once statically indeterminate. Once statically indeterminate. Okay, so remember that whenever we talk about redundancy, it means the number of unknowns minus the number of equilibrium equations. The equilibrium equations must be supplemented by additional equations. As we said in the previous video, that the indeterminate structures, we are going to find the unknowns larger, or the number, I mean that the number of the unknowns is bigger than the number of the equilibrium equations. So this means that we want to put some more equations. It will not be equilibrium equations, it needs to be like other equation, supplementary equations. Okay, so in an approximate analysis, remember this is an approximate analysis, the additional equations are established using engineering judgment. Yes, what is the meaning of engineering judgment? That commonly whenever that we solve such a kind of frames, we found that there are some values for some internal forces that can be like assumed with a great deal of reliability. Like the axial force and the girder, for example, it can be assumed 0 in this case. Okay, whenever that we use this, 0 can be used as an assumed value for the axial force in girders. So this is based on engineering judgment based on using and analyzing and studying several frames that is having similar characteristics of the frames of the buildings, and we found that we can assume based on this this value of the internal axial force, for example. Okay, so this is number one, which is important to remember, which is the redundancy. Let's go to these two assumptions. We have two assumptions actually here. Assumption number one is the location of the points of inflection. This is number one. And in this case, whenever that we have a frame, whenever that we have a frame, something like this, for example, whenever we look to one bay of the frame, which is going to be enlarged here, what we are going to see here is that we have like two columns and we have a girder, From our understanding, of and from our experience from solving many similar frames, we found that the frame is having this approximate bending moment diagram for similar building whenever that it is hinged, and there is like lateral load is being applied, lateral load is being applied. We found that in the middle of the girder at point E, the value of the bending moment is, as you can see here, 0. What is the meaning of 0 here? This means that we can introduce a kind of internal hinge at the middle. We can introduce an internal hinge of the middle, an internal hinge at the middle. Remember that this point, which is the 0 bending moment, is going to have another, we can say title, which is the point of inflection. The point of inflection means that the point where the bending moment is going to be 0, the point where that the elastic line of the structure is going to be inflected, as you can see. It is something like the point at which that this is the elastic line from the left, this is the elastic line from the right. So we call this inflection point. Commonly, whenever there is an inflection point in the displacement, it will be associated with 0 bending moment. 0 bending moment, commonly. So from here, we can draw a kind of additional equation. So we can state it like this. Inflection, internal hinges are inserted in the indeterminate structure at assumed location of inflection points to obtain a simplified determinate structure. What is the meaning of determinate structure? This is, as you can see, we have hinge at A and hinge at B. It means that we have like 2 reactions at A and 2 reactions at B, right? So it is, what is the number of unknowns here? It is 4. How many equilibrium equations do we have? It is 3, right? We have 3. So 4 minus 3 equals to 1. So it is 1 statically indeterminate. So this means that we need to put additional supplementary equation. So we are going directly to what? Adding this. We added an internal hinge because we are sure that the moment is going to be 0 at this point of inflection. This means that there is a supplementary or an added equation, and this equation is going to be only one equation, which is going to solve one unknown. So in this case, we have 4 unknowns, and we are going to have 4 equations, 3 equilibrium and 1 coming from the internal hinge. Then we have transferred the simplified indeterminate frame, as you can see here, to what? To a simplified determinate frame. That's the meaning. Each of the internal hinge provides one equation of condition. We call this equation of condition. or condition equation. Okay, the internal hinge is condition of equation. Okay, so now this is the first assumption. The location of points of inflection, okay, can be introduced at the points where moment is going to be 0 or where the inflection of the elastic line of the structure is going to be introduced, as I have explained here. Okay, so we have done this now. Okay, let's go to the next point, which is the number of inflection points assumed should be equal to the degree of indeterminacy. Do you remember that we said in our structure it was 4 and we have 3 equilibrium equations, so the degree of indeterminacy is 1. This means that we need to put additional equation, which is the equation of condition, which is at the point of inflection. We're going to pick to make this, to put it here. Okay, so if we have more equations, more indeterminacy, if we have 2, for example, so if we have our case, let's assume that this is not hinge, it is fixed, for example, then we're going to have, instead of 4, we're going to have like 5 minus 3 equals to 2. In this case, we are going to apply only one equation of condition at the middle of the girder, and we need to think about another equation of condition, okay? It is not available now to explain it, but at least this is the case for this specific structure, that it is only one statically indeterminate, and whenever that we put or insert the point of inflection of internal hinge here, then it will work for us, and we are going to have a simplified determinate structure. The inflection points should be selected such that the resulting determinate structure must be what? Statically and geometrically stable. This means that we need to fulfill one important condition related to stability. This means that this indeterminate frame, when we are going to make it determinate frame after putting the internal hinge here, it must be what? Exactly stable. Okay, it should be stable, statically stable and geometrically stable. If you want to know more about this, already we have explained this before in the class of structure analysis, the stability related to statics and geometry. Okay, so in our case, this is a kind of statically and geometrically stable determinate structure. This is the simplified determinate frame here. Okay, so now let's conclude the first assumption, that we are going to exactly insert a point at the point of inflection, we are going to insert an internal hinge, and this internal hinge would provide us an additional equation. This is number 1. Number 2, when we add this internal hinge, it should maintain the determinate structure to be stable, statically and geometrically. Okay, so this is the first assumption. Let's go to the second assumption. The second assumption is related to the distribution of forces among members and reactions. As we said, we are using our engineering judgment in order to simplify our indeterminate structure. So now, based on our engineering judgment, we said that there is an internal hinge. This is already has been discussed in the previous assumption. Now, the second assumption is that from our experience, we found that the horizontal reactions AX and BX can be assumed equal. So this AX and BX is going to be equal. These two ones going to be equal. Okay, that's very nice. That's another kind of equation that we have put here based on our engineering judgment. Okay, the two horizontal equations at point A and point B would be equal. Okay, as you can see, if we have the external load P is going to be here. Without doing anything, we're going to say that the horizontal reaction at Bx is going to be P over 2, and at Ax it's going to be P over 2 as well. Okay, so the two assumptions that we have explained now, we can use them like individually, or they can be combined together. They can be used individually or can be combined together. Okay, let's go now to the analysis of vertical loads, which is the first type of loads that is going to be handled in our course, vertical loads. Okay, let's go with the vertical loads, putting in our minds the assumptions, the two assumptions. We are going to insert internal hinge at the point where that inflection points, or at the point where the inflection point is going to take place. Okay, and number two, there's some condition with the first assumption that our structure should be always stable geometrically and statically. And the second option, or the second assumption, that we can share the horizontal forces at the supports, or we can say that they are like equally sharing the external loads applied on the bay of the frame. Okay, let's go to the vertical loads and see how we are going to apply our assumptions and how we can analyze our frame. Okay, so remember, what is our main goal? The main goal is to analyze the structure, meaning to draw the shearing force diagram, the bending moment diagram, and the axial force diagram. Okay, these are the three things that we want to highlight or to have at the end. Okay, now let's go to another thing, which is this frame that we have. We have a frame here, as you can see. It is loaded with vertical load W, or distributed load here, which is W, here in the first floor and the second floor. And here we have fixed support at A, B, and C. We have different bay length, L and L1. We have different floor height, H and H1. So this is the building frame that we have. First of all, the first thing that we are thinking about is how to calculate the indeterminacy, or the degree of indeterminacy for this frame. There is a simple rule that we have explained in structure analysis course, which says that whenever we have a multi-floor frame like this, then the degree of indeterminacy is going to be, we want to know the unknowns first. Okay, we want to know the unknowns. So the unknowns is going to be related to each girder. Each girder needs to have three unknowns: axial force, shearing force, and bending moment, right? Times the number of girders. How many girders do we have? We have 1, 2, 3, 4. So we have 4. So this would equal 12 unknowns. How many equations of equilibrium that we have? Commonly we have 3, right? So this is equation of, let's assume EE means that equation of equilibrium. So it is 3. So we have 3, and we have here the unknowns. So the degree of indeterminacy, let's put it DI, okay, degree of indeterminacy equals to 12 minus 3. So we are going to have like 9 degrees of, okay. So this means that we need to think about this. We need to think about this. In this case, we need to overcome this problem, which is the degree of indeterminacy in our case. Remember that I didn't include here, actually we have like external reactions as well, which is we have like 3 different, if you can see here, 3 different unknowns at each support, okay? So this is one of the things that we need to consider in our case. But I want you to recall something that we have explained before, that the degree of indeterminacy of a rectangular building frame with fixed support is equal to 3 times the number of girders in the frame, provided that the frame does not contain any internal hinges. So the degree of indeterminacy directly in our case here for rectangular frame is going to be 3 times the number of girders that we have for a frame that is fixed at the bottom. Okay, then this means that each frame there are 3 unknowns. This means that for each frame we need to what? Yes, assume 3 different equations, okay, in order to make it determinate. Okay, and this is what we are going to make actually here, which is assumption are made for each girder of the frame. We are going to assume that for each girder of the frame, if we are going to take this girder, we're going to put it here, we're going to assume that the girder is going to have inflection points here and here. So we have one inflection point. This means that one equation, and it has another inflection point, which is another equation. Okay, this is the second equation. And we are going to assume that from our experience that the axial force in the member is going to be 0. Okay, so we assumed that the moment at this point, which is the inflection point from our experience, is going to be 0. So we can introduce internal hinge here, and also here is going to be 0, and we are going to introduce the axial force is going to be 0 as well. So we have 1, 2, 3 equations have been introduced here, and this is what I put it here. The inflection points are located at 1/10, okay, of the span from each end of the girder. So if you are going to look here and here, actually it should be between 0, 0 and 0.211 the length. So it should be between this, okay? This is the case of the fixed case, and this is the simply supported case. So it should be halfway through actually. So we used, or the people commonly use 0.1 L, I mean, okay? 0.1 L. Okay, so this is the 3 different equations of condition that we're going to use. Let's go again between to explain more about this girder and how we can use it. So here, as we said, this is the inflection points. Okay, in case of the fixed condition, totally fixed condition, as we said, this would be 0.211. Okay, but because of the frame, because the real frame actually it is not fixed condition totally. It is sometimes if it's loaded different ways, then it is going to be different moments. So the assumption made here is for the case of fully fixed, but our case or the way of the approximate analysis that we are going to use is going to assume that this is going to be 0.1 L. Okay, so this is what you should use in your analysis, 0.1 L from now on for the approximate analysis of vertical loads. Okay, so the point is, as we said here, the moment is going to be 0, 0. Okay, the moment is going to be 0 here, and the axial force is going to be exactly, the axial force is going to be 0 as well. Okay, then we are going to deal with this portion, which is the internal part, as if it is supported on the other cantilever parts of the frame. And this is going to be shown clearly in the next slide, okay? That what are the steps for your analysis? From now on, you need to have 2 steps of analysis. Now, let's go to the simplified determinate girder. It is going to be like this. We assume that we introduced what? Internal hinge here and internal hinge here, okay? Right? And this is the part of the frame, as you can see here, and this is the part of the frame. So we assume that we're going to take the free body diagram of this. This is the free body diagram here. This is the free body diagram of the inner portion of the inner portion. Okay, so here you're going to find that the distance, as we said, is going to be taken 0.1 L from now on for our approximate analysis. And we are going for step 1, we are going to determine the shear, which is after separating the internal part, which is this one, we're going to get the shear, which is the reaction at the support. We have this point, this is W, and this is 0.8 L after subtracting 0.1 L from here and 0.1 L from here. Then the reaction is going to be exactly 0.8 L times W over 2, which is 0.4 WL. And because of symmetry, we are going to have 0.4 WL here as well. Then the second, this is the first step, okay? The first step is obtaining this shear force or the reaction. This shear force is going to be we're going to reverse it on the portion of the frame, which is going to be 0.4 WL here and the same also from here. Okay, so in this case, our frame, if you look deeper, sorry for this. Okay, if you look deeper, you're going to find that here, this is how it works. So let me make it larger. So here at this point, there is force. Let me put another color so that it would be clearer for you. Here there is 0.4 WL, and there is some distributed load here, which is W, right? Okay, so this means that we want to know the moment here, which is going to be the second step, okay? So the second step is going to be, so the moment here is going to be exactly 0.4 WL times this tiny distance, which is going to be 0.1 L. So it is going to be 0.1 L, okay, over 2, right? 0.4 W. Sorry, this is, this is 0.4 WL times 0.1 L, which is the moment coming from the shear force, plus another moment, which is the W times this small distance, which is 0.1 L. So, yes, this is, okay, sorry for this. Let me erase this part, okay, and rewrite it again. So it is going to be plus W times 0.1 L, right? 0.1 L. This is the force times 0.1 L over 1. So it will be like this, right? This is what would give us the moment here. Okay, this is the moment here, which is going to be, if you sum them up, you're going to find it is going to give you 0.04, which is this one, 0.045 WL squared. Okay, and of course, at the end, you're going to find that here and here, it is the reaction of the support at or after putting this, because of the symmetry, we have the axis of symmetry here. So this would be WL over 2, WL over 2, where this is the bay length, okay? So remember these two steps very well. Number 1, determine the shear after separating the inner part of the frame at the internal or inserted internal hinge. Calculate the reaction from this inner part and reverse it on the cantilever, okay, of the main frame, and then calculate the second step, which is the moment. The moment is going to be the force times the arm, okay, the force times the arm, and after that we are going to have the distributed force here times this distance times half of the distance to give us the additional moment. Okay, that's it. This is how the frame is going to look like. So we're going to make this for each frame, for each bay. So this one here, this one here, here, and here. And every time this distance, as we said, it is 0.1 L as is given here. based on the span. Okay, so if this is the span L, this is 0.1 L. If this L1, this is 0.1 L1, and so on. Okay, I think that you have had an idea right now, but let's go and make like another example that would make everything clearer for us. Okay, we have a frame, as you can see here. This frame length is 30 foot or 30 feet. Okay, let's use the 30 feet here each, and we have 2 floors loaded with 1.5 and 1.5 kips per foot. The floor height is 15 feet, and it is a typical rectangular building frame. A typical rectangular building frame. Okay, so now let's go and see what are the steps, what are the strategies that we are going to use. First of all, you are going to look here at each floor. You are going to put your internal hinge. Okay, that's right. And you know the distance for each one. So here, this distance is going to be exactly, it is going to be 0.1 times 30. 0.1 times 30. We have the distance here, 30. This is 3 foot. So we are having this distance to be 3 foot, and it will be the same also for this one because we have the same L here. Okay, and for all of the girders, we have the axial force 0. The strategy of the solution is to separate the inner part for each bay and to calculate the shear and then to calculate the moment. Okay, let's go to this. Oh, yes, as you can see it here. I took this one, which is one of the frame, one of them is going to be typical. So here I took the inner part, which is going to be 24 here, as you can see it here. From this we can obtain the shear force or the support reaction at this one, which is going to be the 1.5 times 24 over 2. It would give us 18. This 18 is going to be reversed here. Exactly. That's right. And after that, we are going to calculate, if we're going to talk about the, for example, the lift part here. Okay. So we want to know how much is this, which is the total vertical force or reaction at the point of the frame or the joint of the frame. So how we can get it? Exactly. From the equilibrium of this joint, SL equal 22.5. How we got this? Yes, we can get it from here. Let's take the summation of Y vertical force is equal to 0. And let's take the vertical reaction or the vertical force to be positive. Then looking to here, we're going to have SL, which is going to be positive, heading up, minus 1.53 from where this one? Exactly. This is the portion of the distributed load, having minus sign, and this is minus 18, which is coming from the internal portion, which is this one. Then we're going to get the shear at the lift joint is going to be 22.5, and it is heading up, as you can see, 22.5 heading up. Okay, here. Okay, now let's get, this is the first step. If you remember, the second step is going to be exactly the moment. What is the moment? We're going to look at the same point here. Okay, so as if that we are talking about this point, okay, some point here. It is loaded with some force, and there is 18K is here. Okay, in this case, let's use another color. In this case, this 18K, and this is the 1.5K per foot, we want to know the moment. It seems that this distributed load is going to make force down, and we have the force coming from the 18K or 10 kips coming from the internal part. Then we can say that taking the moment at this point, okay, at this point, and making the counterclockwise to be positive, summation of moment at point L, which is the lift, equal to 0. This means that ML, so where is ML? Let's assume it like this. This is ML, okay, minus 1.5, this is 1.5, times this distance, which is 3 foot, times half of the distance, which is 3/2. This is 3/2. Minus 18 times 3. Minus 18 times 3, equal to 0. From here, we can find that ML is going to assume this value, and it is what? Exactly, as we have assumed it. It is counterclockwise because it is positive here. Okay, so now this is what we have obtained. This is for the lift part. So for the lift part, we have obtained the S lift equals to 22.5, and the moment at the lift equals to 60.75. This is for the lift. Because of the symmetry, we are going to have, we have a symmetry here. Because of symmetry, we are going to say that the right shear at the frame joint is going to be the same, 22.5 K, and the moment is going to be the same as the lift one, which is going to be 60.75. So this is what we have concluded at the end. The shear at the joint at the right and the moment at the right joint is 60.7. Based on this, we can draw the shear force diagram, as you can see, and we can draw the bending moment diagram. At the joint, the value of the shear force is 22.5. Okay, it's 22.5. Sorry for this. 22.5. Okay, and at this point, which is the internal hinge, it is how much? 18. And it is going from the lift and going up. This means that it is positive here. And then, because the distributed load, then our shear is going to be linear and going like this. And there is axis of symmetry here. And for the bending moment, we're going to start with 60.75. Remember that it is, as we said here, this is the value here, 60.75, and it is counterclockwise. Actually, here this is the American style, but for you can draw it like this. I prefer it, even in the exams and so on, you can prefer it. I prefer to make it like this, which is negative on the top of the girder and positive on the bottom. Okay, so this is the value here. It is going to be 60.75, which is negative here, and here the same. We have axis of symmetry here and here, and the value here is going to be, you can get this value from WL squared over 8, and you can subtract the value of the moment at the support, which is 60.75. You're going to obtain it 108. Okay, this is 108. I hope that you can understand this. It is very easy actually, and you are, as I said, you are going to find that whenever you apply the two assumptions, you're going to find that the analysis of the vertical loads for the rectangular building frame is going to be a systematic procedure. You're going to find it super easy and no need to exhaust yourself based on what we have said. Now let's go to the final thing, which is the in-class assignment. So I think that this is an in-class assignment. You should solve this during the class. So I strongly recommend for you right now to stop the video and try to figure out this example or this problem and try to solve it by your own or by yourself, following the explanation that we have explained, okay? And I think that it's simple enough for you to solve it within less than, I guess, like 10 minutes, okay? Less than 10 minutes. I think it's less than this. But anyway, stop the video now and try to solve it by yourself, and then come back again, pause the video, and after solution, come again and play the video and see what is the result of it. I'm going to give you the results, and I'm going to give you some hints about the results only. So this is the results. I hope that you have worked it out. So actually, our case is only one. There are symmetry here. So let's have the red annotation. We have an axis of symmetry, so we're going to work one of them. So if we work with the lift, for example, here and here, we are going to introduce the internal hinge, right? Then we're going to have our structure to be similar to this. We're going to have the inner part, which is this one, internal hinge here, 30 kilonewton per meter. Then we are going to calculate, yes, the shear force here, which is going to be 72. Actually, the shear force at the lift, if we say this is the shear force at the lift, is going to be 30 times 4.8. This is 4.8 over 2, which equals to 72 going down. So this is the first part of the first point on the shear diagram, shearing force diagram. And then to get the maximum value here, it is going to be 72 plus 0.6 times 30. Actually, this part is going to be 0.6 because it is 0.1 L, okay? And we have L, which is 6 meters. So it is going to be 0.6 L. It is going to be 0.6 meters. So we have 90 here and we have 72 here. From these 2 points, you can draw the shear force diagram very easily because we have an axis of symmetry. And for the bending moment, you are going to look to the bending moment here, which is M at the lift, is going to be 72 times 0.6. If we are going to put it here, it is something like this here, okay? Assume the moment like this. So we have here the force, which is 72. We have some distributed load, so that we have another color here, which is going to be 30 here. Then 72 times 0.6, this gives us the moment from the shear lift, plus 0.6 to the power 2 over 2 times 30. This is coming from the distributed load. This would give us 48.6. 48.6, which is this value. And then this amount, we can obtain it. It is WL squared, which is 135 minus 48.6. You are going to give it. This is the bending moment diagram. I hope that you have solved it well, and I hope that you are able to get the same shearing force diagram and the bending moment diagram. Let's wrap up our video today by giving you a home assignment, and I hope that you can. I think that this is the home assignment. Okay, sorry for this. I think that I didn't put the right. Okay, yes, this is if you what I can say, if you didn't solve it well, okay, I think that for you can try it again and solve it by yourself without even looking to the what I have showed you, and try to solve it by yourself. But instead of using 30 here, it should be like 20, and instead of using 4 meters here, make it 5, and then this would be the home assignment for you. So it will be very easy, I think, for you to use, because the same almost the same geometry, but small different values. I hope the best for you. Thank you, and see you in the next video, and wish you good luck.